All right, let's get started. We're now going to look at binary search. So public class binary search example. What exactly does binary search do? Well, let's look. Public static void main string args. Let's go ahead and create ourselves an integer array. Call it R, and then equals, say 1, 2, 4, 6, 8, 9, 11, 13, and 15. All right. Very easy search is called linear search. Linear search. What does linear search do? All it does is goes through every single element in the array. For I equals 0, I is less than r dot length, I plus plus, and what does it do? System, too much habit. If, we're just going to go through every single element in there. We're going to say if r sub I equals what we're looking for. What are we looking for? All right, so we need something called a key. So int key equals, let's suppose we're looking for the number 11. So let's say the key equals 11. So we're going to go through the entire thing, and we're going to say if r sub I equals 11, then we will go ahead and return the result of where it is. So int index equals -1. And then we will print, if we find it, we will say set index to where it is. We'll break out of the loop, and at the very end, we'll say system out println index equals, and then index. Okay, so what does this do? Well, for a for loop, let's move this down. There we go. I've got the entire array here, 1, 2, 4, 6, 8, 9, 11, so forth. And we're looking for 11. And -1 means we haven't found it yet, because at this point we haven't. So now we're going to go through the entire array, all through there. And for each element, array sub 0 is 1. Is 1, array sub 0 will be replaced by 1. Is 1 equal to 1? No. Is 2 equal to 1? No. Is 4 equal to 1? No. Is 6 equal to 1? No. No, it's not. Is 8 equal to 1? No. Is 9 equal to 1? No. Is 11 equal to 1? Yes! It will set the value of I, which is the location of 11, and then it will break. So that's 0, 1, 2, 3, 4, 5, 6. So that's at the 6th spot. So index will equal 6, and then it'll break out. To break will means, to, if you recall, will stop execution of the current loop. Okay, then it'll print out index. If it didn't find it, it'll simply be -1. If it did find it, it'll be the correct answer. So let's save it. Let's put it where we always save it, and then let's run it. So index equals 0 because we forgot to set this back to r sub I. Okay, now that we've got it right, hey, index equals 6. 0, 1, 2, 3, 4, 5, 6. Yep, that's at the right place. Linear search. Not bad. But the bad problem is, let's suppose there's like 1,000,000 elements in here. If there's 1,000,000 elements in here, this will be super slow. But we're going to come up with something called a binary search. And I prepared this for us. It compares the binary search to the linear search. The worst case scenario is if there's 10, let's see here, let me get rid of these zeros, there we go. In the worst case scenario with linear search, if there's 10 elements in the entire array, I'll have to look through all 10. If there's 100 elements, I have to look through 100 elements. If there's 1,000,000,000, I have to look through all 1,000,000,000. That's very inefficient. The binary search, this is log base 2 of 10. The actual, there we go. and 10 here, and 100 here, and this is the Excel equation for you. So it's taking the floor because we don't need the decimal place. Log base 2 of this element right here. So if there's 10 elements, we only have to look 3 times to find out that it's not there. If there's a billion, we only have to look through 29 times to find out that it's not there. If it is there, then it'll be less than this. Less than or equal to this number, and the same for the linear search. How does binary search actually work? Well, let's suppose we have some numbers here. I'm going to have a 1, 2, 3, 4, 5, 6, 7. All right, let's make these small. We'll make them all the same size. There we go. Now, let's suppose we're looking for key equals 2. Well, what's the length of this? The length is, there's 1, 2, 3, 4, 5, 6, 7. So the length equals 7 of these. Pretty cool. Now, what is length divided by 2? Well, that equals 7 divided by 2, but we don't care about the decimal place, so it's going to be 3. Well, okay, let's look at put indices here. We have 0, the wrong button. 0, there we go. 1, 2, 3, 4, 5, 6. And I have no idea why that's coming out that way. But whatever, that's a 0. All right, so we look at this and saying, all right, 7 divided by 2 is 3. Let's look at this one. Is this is the midpoint right here, is this equal to the key? Does the value 4 equal 2? 4 equal 2? No, it doesn't. 4 is greater than 2, so therefore we only need to look at the rest of this side, on the left side. We don't need to look at this side at all. We've cut the thing in half. So at this point, we can completely wipe out half of it. All right, let's see here. We can wipe out all of this now because this is the only part we're looking at. Cool. All right, so that's not the mid anymore. This is the mid. And mid is 1. All right, so is this equal to it? Hey, yeah, it is. We got it right away. So it only took 2 searches for a length of 7 to find it. That's not bad. Let's do it again. Let's get rid of our mid, and let's make all this black again. All right, let's say we're now looking for the number 8. It's not there. Well, the mid here is still the same, so this is the mid. And we're saying, okay, is 4 equal to 8? Well, no. So we know that everything less than, and including this one, is not part of it. All we have to look is here. All right, we'll take the mid, move it to there. All right, there's only 3 elements. The middle is 6. Is this equal to here? No. So we know that that and everything below it is not it. So let's move it to here. All right, mid, is this it? No, that's not it. So we know that it's not in the array at all, and it only took us 1, 2, 3 times to find out that the element we're looking for is not in there. So binary search, it's pretty cool. Cuts it in half every single time. So we're going to say result from linear search, index equals here. And now let's do the binary search. The binary search is a little bit more complicated, but really easy code. We'll simply say index equals arrays.binary search. You pass in the R, the array, and the key that you're looking for. The key we're looking for is 11. So is it there? Is 11 in there? Yes. According to linear search, it's going to give us a 6. So does binary search do it for us too? Binary search. See how that runs. And of course, I spelled something wrong. Cannot find arrays. No, I didn't spell it wrong. I didn't import it yet. Silly me. So import java.util. u tilde star. Less typing. Compile that. Works. Ta-da! Very nice. The binary search on this size, 1, 2, 3, 4, 5, 6, 7, 8, 9. It would have looked at maximum 3 times to find that it's not there. But here, with the linear search, it would have looked at the whole thing. So let's change up the key. Let's look for 18. And there we go. I forgot to set this to key. I was still looking for 11. Sorry about that. Okay, yep, the passed to -1, and the binary search gave us a -10. Any negative numbers from binary search means it's not there. So binary search is a very fast, very efficient way of searching through things. The only downfall of binary search is that the array must be sorted. With linear search, it doesn't have to be sorted. Linear search is super easy for you to implement yourself. Simply do a for loop, check to see every element is there. Binary search is really easy too. You just call it, and it returns the index of where it's there. If it returns a negative number, then it's not there.